Okay, so last time we talked about permutations, combinations. We had given one example of each where we had a 50-person grouping to pick from, and we picked 2 people. When the order did not matter, that was a combination. If the order of those contestants on that game show, which is the problem we had, mattered, then it was a permutation. So we're going to see another real common use of something that is a permutation or a combination. All right, so we have a standard 52 card deck. I know you guys don't like those cards. Had a conversation with a couple of you that they do not make you happy campers. But you know about them a little bit more, hopefully, if you aren't comfortable with them than you did before a couple weeks ago. So the first issue that I want you to think about, and it doesn't have to be a 52 card handed cards. You can play Uno, and this will still have the same process. So what I want you to think about first is, does the order matter? When you're dealt a hand of cards, does the order matter? No. In fact, what's the first thing most of you probably do when you're dealt a hand of cards? You move things around, don't you? You put them in whatever order for whatever game it is that you're working. I don't care if it's Uno, or if it's poker, or if it's face 10, or if it's hand and foot. These are games we play at my family's house. All these games, Skip-O, the order doesn't make any difference. The first thing you usually do is you sort of reorganize and reformulate what's there into a way that makes sense for you for that game. Okay, so the order doesn't matter, which means what do we have going on? So I think I heard Mackenzie say, what do we have going on? This is a combination, exactly. Okay, so since the order doesn't matter, we're going to be working with combinations when we're working with these card problems. Every problem we do is going to be a combination. All right, so let's do a few here now. We have a 52 card deck. Every card's different. So that is something unique about our 52 card deck as opposed to like a Uno deck, is that every card's not different in those. But in our 52 card deck, every card really is different. Okay, so that's why we're using this as a combination example, is because of those differences. How many cards am I choosing from? 52. And this is going to be a hand that has how many cards in it? A 5-card hand. Okay, so again, that's specific to a certain kind of game. Not every game has a 5-card hand. We could do something that had a 2-card hand and do the same process. But this is a combination with 52 choices, and I'm choosing 5 of them. Does that make sense? And the C is for the combination part of what I'm doing. Now you had a formula, so flip back if you don't remember it off the top of your head. What goes on top of the formula of a combination? The 52 will. What goes on bottom? Okay, so when I do a combination, I have 2 items on the denominator, 2 factorials. The first factorial, at least in the order that we did it, is 52 with the outer number, the larger number minus the smaller one, 52 minus 5. And in the smaller number, the number I'm actually choosing the 5 factorials there as well. Now we had done one example last time, but we hadn't done very many yet of this process. So what we had talked about is that we could, well, first of all, let's recognize what's 52 minus 5. 47. Okay, so I can actually take that 52 and I can write the 52 out until I get to where? So in order to cancel out a factorial, it doesn't just have to have something in common, it has to be identical. So once I got to this 47 factorial, it is identical to a 47 in the denominator. Now I'm not going to have a 5 factorial in the numerator because I'm going to cancel out the 47 and down. So the best thing I can do at this point is to simply write out the 5 factorial. If you try using a number as big as 52 factorial in your calculator, some of your calculators will do factorials, it will not be able to calculate it with all the decimals across your screen, and it'll turn into scientific notation, which ends up being unhelpful in particular case we're working in. So my 57 or my 47 factorial cancels. If you want, you can multiply across the top, multiply across the bottom, calculator, divide, you can do that. Another thing you can do is you can start reducing some things, which is a nice clean way of doing it. In other words, like this 5, it could cancel with what? 50, so the 50 would become a 10. How about the 4? What could it reduce with? 48. And again, there's multiple ways of doing that, but the 4 reducing with 48 makes the 48 become a 12. All right, so what do you want to do with that 3? 3 with which one? 51, okay? So 51 divided by 3 is what? 17. How about the 2? With the 52? All right, so the 2 reduces the 52 down to a 26. So if we do it that way, and again, there's other ways that you could have reduced things. The reducing that we have right now is 26 times 17 times 10 times 49 times 12. What does that give me? It's 2 million something. Say it again louder for me.
598,960.
Awesome. 2.6 million about, right? A little over 2.5 million different hands of cards you can be dealt. How crazy is that? That's a lot. I mean, that's a lot of different hands of cards. All right, so taking this idea, we're going to put some restrictions on it next, okay? So we still have our 52 card hand, 52 cards to pick from. We still have a 5-card hand. But what we're going to do for part B is we're going to find out how many different hands we can have that contain all diamonds instead. Because I don't really care that there's 52 cards. What I want to see is how many different cards it can have or hands it can have that have all diamonds in them. So what's going to change when I set up my problem? The total number, the 52, right? So instead of having a 52 at the beginning, what am I going to have? A 13. Why 13, Brendan? So there's 13 diamonds, right? There are 13 cards that are diamonds. And I want to choose 5 of them because I still need a 5-card hand. So just getting all diamonds is a descriptor that means a lot of different kind of hands, right? I could have a hand that's all diamonds and it have a variety of different things in it in terms of the number of cards. So what goes on the top of this? Good, 13 factorial. What goes on the bottom?
13 minus 5.
Okay, and what's 13 minus 5? 8. Okay, so that's an 8 factorial on bottom. So I can take my 13 and I can write it out until I get to, and I'm going to stop at 8 because that's the largest number I can stop with and actually get something with the denominator is identical to the denominator. So 13, 12, 11, 10, 9, 8 factorial. I have another 8 factorial, that's in the denominator. And then what do I do with my 5? Same as last problem, right? I just write it out. Alright, so what reduces? Okay, first the 8 factorial. Let me do that first. And then you want to do the 5 and the 10. Okay, 5 with 10 makes the 10 become a 2. Now what? 4 and 12. What does the 4 make the 12 become? 3. 3. Now what? If you want, but couldn't you just cancel the 3 and the 3 and the 2 and 2? You guys are trying to cancel them all out uniquely, but couldn't I just cancel this 3 and this 3? And this 2 and this 2? It doesn't matter. But you could, right? Then you don't even have 5 numbers on top anymore. You actually have how many? 3. 13 times 11 times 9. If you reduce differently, it doesn't matter. It still gives you the same result. What's the 13 times 11 times 9? Is this what you told me, Heather? Okay. 1,287. That's how many different 5-card hands contain all diamonds. Okay, part C now. What's different specifically in the directions at the very beginning of part C than part B? The word says probability. Finding the probability of something is not the same as finding the number of something, is it? But it is related. So what do we mean when we say probability? Okay, so you're giving me the answer already, Brennan, that's fine. So out of all the ways we get anything to happen on bottom. So my probability of getting all diamonds is the number of ways of getting all diamonds. It's the number of all diamond hands divided by the number of all hands. That is, how many ways can I get any hand? So Brendan already gave me the answer. He said the number of all diamond hands, which was my part B, was my 1287. And the number of ways of getting all hands, which was part A, which was excellent. And would somebody do that division for us? You don't need to keep it in a decimal form. You can turn it into it. I mean, you keep it in fraction form. You can turn it into a decimal. What do you get? It's a really small number. So if you were doing this problem on a test, I'd tell you how many decimals I went into. This is fine. So, like, it's never going to happen, right? It does happen. It's pretty rare. It's very uncommon. That's why when people play a game where they're trying to get something specific to happen on all the 4 cards or all the 5 cards or all the 2 cards or whatever to match, these are unlikely events. And so they have a very uncommon or very small probability. So this is a less than 0.05% chance. That's what that works out to. All right, let's do another one that's not cards, but has the same feel to it, okay? So we're going to select a committee. It says a committee of 3 people is selected at random from 7 seniors, 5 juniors, and 3 sophomores. This one jumps to gun right away. It says, what is the probability that the committee contains all seniors? So we're actually not given the part A and the part B like the last problem did to sort of develop into part C. We still have to do it, don't we? Yeah. So in order to get the probability of all seniors, it means I need to figure out the number of ways to get all seniors. And I have to find out what the total number of ways are to form the committee, or form any committee. Does that make sense? It's the same problem, it's just I've started with part C of like the last problem. So the first thing I got to do is figure out how many ways to get all seniors. So how do I get, let me do this kind of as a second step. Let's do the number of ways of getting seniors. It's the number of all senior committees. How do I get that? Okay, so slow down. How many seniors are there? 7. There are only 7, so don't tell me 15. Because 15 is all the people, right? Not all the seniors. And if I want a committee to contain all seniors, this is like wanting my hand of card to contain all diamonds. I only have 7 seniors.
7. C. 3.
3?
Well, I don't know.
Yeah, because it
There
has
are 3 people.
from that 3. 7C3. There are 7 seniors, and 3 of them, we want 3 of them on the committee now. So this is 7C3. All right, so how do I find 7C3? So, and 7 minus 3 is simply 4. So I could write my 7 out until I get to where? I could, or I could stop at 4, couldn't I? I always stop as soon as I can. So I'm going to start at 4. And then I have the 3, 2, 1. So my 4's cancel, 4 factorial, excuse me, cancel. Now what?
3 is 6.
The 3 and the 6, so the 6 becomes a 2.
2 minus 2.
And then my 2's cancel. So what do I end up with?
7 times 5.
Which is, okay. So there are 35 different all senior committees that could be formed. There are 35 different ways I can get a committee that has all seniors. Okay. Now, how do I get the number of total committees? What do I do? I'm sorry. All the people. So how many people are there? That's the 15 you guys were going to do earlier, isn't it? So I have 15 total people that are sort of interested in being on this committee. And I still only have 3 people on the committee, so it's still choosing 3 of them. I just can choose any of the 15 of them, not just the seniors in this case. So what's my numerator look like?
15 factorial over 15 minus 3 factorial, 3 factorial.
That's right. Good. And then 15 minus 3 is 12. So I'm going to stop at the 12 factorial, right? So I have 15, 14, 13, 12 factorial, and then 3, 2, 1. Okay, so the 12 factorials, those cancel. What else? 3 and 15, 15 becomes a 5. 2 and 14, and 14 becomes a 7. So looking up here now, you have 5 times 7 times 13. What in the world does that give you? 400 what? 55. All right. 455 committees. Far cry fewer than the 35. But the question I was supposed to be working on was this probability question. How do I get the probability of all seniors from this work? $35 over 455, exactly. And then we'll turn it into a decimal. What do we get?
How many decimal places?
Let's go with 3 non-digit zeros. So if you start with zeros, that's fine, but then go 3 numbers after that. The first one's a 0. 769. And it'll be real clear on the test if I give you something how many decimals I want. So 0.0769. About an 8% chance. That's what that number looks like, right? So you can multiply by 100 and get your percentage. So about an 8% chance that the committee is all seniors. All right, next question. Sounds like it would be harder, but it's actually really easy after we did the first one. What's the probability that it has no seniors? In fact, yeah, the probability that has no seniors.
455 minus 35.
Or is it?
You can just divide, or you can just subtract the percentage.
No, from 1. Are you sure? You need to be really careful in the wording. They're not mutually exclusive, they're mutually exclusive, but they don't contain every possibility. I have the all senior committees, and I have the no senior committees, but did you leave anybody out?
Some senior.
There are some committees that contain both, don't they? Some seniors and some non-seniors. So we can't just do 1 minus on this one. What would it have to say for me to do 1 minus?
Isn't made of all seniors.
You can say isn't made of all seniors, or you can say not all seniors, right? So if this question said, what's the probability of a committee that's not all seniors? That would be 1 minus the last slide we had,
So now we have to do 15 minus 7.
which is what? Okay, so we want the probability of no seniors, which means we want the number of ways of getting the juniors and sophomores divided by the number of total committees. But we've already done half of this problem, haven't we? We've done the total number of committees. So there's really only one extra piece to do here. That's the number of the juniors and seniors. So we're going to find the number of juniors and seniors, or juniors and sophomores, excuse me. And so we said there's how many of those? There are 8 that are sophomores and juniors.
So it's 8C3.
For some reason I wanted to write an S. 8C3. Try this again. So it's 8 factorial over
8 minus 3
and 8 minus 3 is
5.
5. So I'll write my 8 down to 5. 8, 7, 6, 5 factorial over 5 factorial. 3, 2, 1. Okay, cancel my 5 factorial. Now what do you want to cancel? 3 and 6, okay. So the 3 cancels the 6 to become a 2. Then what?
2.
Okay, so the 2 and the 2 here can cancel. So this gives me 8 and 7, which is what? 56. So what is my probability of no seniors? 56 over the same 455 as before. So this is just slightly larger. It's really not a lot larger because it makes sense, right? I've got 8 people pick from instead of 7 people pick from. I'm not changing a lot in terms of my final answer. What does my final answer end up being? Yeah, 3 numbers after the 0. 1, 2, 3. That'll work.
Just 1.
There's not a 0, you're telling me. Okay. All right, so 0.123. So about a 12% chance instead of an 8% chance from last time, right? Okay, very good. Go ahead and write down the homework if you need those orange homework problems. We're going to briefly start the next section. Am I good to continue? Is anyone still writing? Okay.